So this integral calculus, so we tend to pronounce it integral rather than integral calculus. There's a notation associated with it. It's an operation that we do to a function. So for example, a function like 5x squared. So how would I say this first bit? I would say, or this notation would be telling me that I want to integrate the function 5x squared with respect to x. So the dx and this symbol here is like the dy by dx. It's notation. The thing that we're actually working on is this. So what it doesn't mean is 5x squared times d times x. This is not part of the function. It's part of the notation. And we'll see that there is a rule, very straightforward rule, to actually differentiate it. And that's going to give us the answer here, which is 5x cubed over 3 plus c. But we'll look at that in a minute. Notice the dotted lines. If I show the integral, this represents the dotted lines, or the lines rather, in your book. So if I've got lines like this, the integral sign tends to go above and below the line like that, quite a big symbol. And so we read it as the integral of 5x squared with respect to x. So x is the variable. And when we integrate, we always end up with a constant added to it. And we'll talk about why that is in a minute. So that's the notation around this integration. What does it mean? The integral is the inverse function of the differential. So every operation that we do to something, and by operation I mean, say, squaring, multiplying by 3, adding a number, square rooting, to the power, the sign of it, and so on. Any operation we do has an inverse, an opposite operation that undoes it. And the integration is like the inverse function, the opposite of differentiation. So if I want to undo a differential, I integrate. So if we know the differential function, we've got an equation with a differential in it. And actually lots of the mathematics that we do in the years that follow these, like the HNC, well, not the HNC, we don't touch it on there, but on the degree program, we talk about things called differential equations, and they just involve these differentials. So part of the process of solving a differential equation involves integrating. So we use integration to undo this differential, to get back to the original function. Something else we use integration for is to find the area under a curve. And that's something you will be concerned with for the distinction part of Unit 4, Assignment 4, but also as the Unit 28, Assignment 5, the calculus part of that, you'll be asked to consider finding the area under a curve, using integration to do that. It's useful because, as we'll see, and we'll talk about more on this later on, but it's worth looking at it now. If I find the area under a curve, so I've got some function that's relating the speed of an object with the time, then if I integrate that, I end up with the area under the curve, which tells me actually the distance travelled, because distance is speed times time. And similarly, as we'll see, the area under a force against distance curve, so this one here, force against distance, force times distance, you might know, is work. I don't know whether you're familiar with that formula. And so if I find the area under a force distance curve, I'm actually finding the work done or the energy used. Very useful, particularly when you're stretching materials and bending materials and stuff like that. How do I find out how much energy is being used to do that? I integrate the function. So it's a useful operation to be able to use. Now, let's look at this. If we look at this function here, y equals 5x to the 4 plus 8, and we differentiate it, we get this. dy by dx equals 20x cubed. If you look at your table of differentials, you'll see that that's true. The rules, the table of differentials tell me to do with a constant. What happens when I differentiate a constant? It's 0, okay? It doesn't matter what this is. It could be any number. It could be a fraction. It could be a negative number. It disappears. When I integrate, which is the opposite of that, then there's no way I can say what that number is because it's gone. So all I can do is say, actually, when I integrate to get back, so when I integrate the original function, that's going to get me back to 5x to the 4, but it won't get me my 8 back. So all I can do is say plus c. And then I'll need further information, and we'll look at this to be able to find out what c is. So when we integrate, we always add this constant of integration. And the reason why it's there is because when we differentiate, that's disappeared. So when we integrate, it reappears. So here's a table of common differentials. Notice this is the differential function, f prime x. And we're getting back to the original function, the integral, it's sometimes called. And the first one is the one I want to focus on first of all. If I integrate a function like ax to the n, the most common type of function, some number in front like 4 and some power like 3. If we integrate that, we follow this rule, and on words at the bottom of your table, you've got it in words, look. What do we do? And this is worth trying to remember. We add 1 to the power, so it's the opposite of differentiation. We don't take away 1, we add 1. And then we divide by the new power. And that's a nice little thing to remember. It almost rhymes, or it's got a nice ring to it. How do you integrate, add 1 to the power and divide by the new power? How do you integrate, George? Right, okay. Add 1 to the power and divide by the new power. As simple as that. Look at the example we've got here. 4x cubed. Add 1 to the power. 3 becomes 4. There it is. And divide by 4. And when we divide by 4, we say they cancel out. So the 4's cancel, and we've just got x to the 4 plus c. Note all of these in this little table have got plus c at the end. Okay? And there are others, the other rules, and we need to have a look at some examples of them and see how they work. Okay? So you've got this table of common integrals. You might like to eventually take this page out of the notes I've just given you and add it to the others. So you've got it together with the differentials and the laws of indices, okay, to refer to. So example, first one, integrate 5x cubed, that's what I'm integrating, with respect to x. Is saying what's the variable in here? X, okay? Integrate with respect to x. Okay, write down what you think the answer is. So next example, integrate 12x with respect to x. Write down what you think the answer is. So in this example, add 1 to the power. So that's a 1, becomes 2. Divide by 2 plus c. 12 divided by 2 is 6. What is on this side? That's the question. The notation around that, because it's okay for differentiating, because it's f becomes f prime. Well, what we do in this case is, because remember we talked about the area under a curve, so it might mean something like the work done or the speed or something like that. At this stage, we're not sure what this all means, so we just have to say the integral of 12x with respect to x is 6x squared plus c. That's sort of how you'd write it, okay? Or if we're going down like this, step by step, down like this, you just put it as equals, because that's what's going on, okay? So it's not always clear what goes on the left-hand side here. So in this example, integrate 5x to the minus 4 with respect to x. Write down what you think the answer is. Answer, 5x to the minus 3 over minus 3 plus c. It doesn't matter where we put the minus sign here, so actually I would put the minus sign at the top. Minus 5x to the minus 3 over 3 plus c. It's just telling me the whole thing's negative, really. So next example, integrate 5 over x to the 4 with respect to x. I've got to do an intermediate step before I can do this, haven't I, Liam? What's that? So the first step, using the laws of indices, this is actually the same as 5x to the minus 4 with respect to x. So as with differentiation, you've got to use the laws of indices, and now it's exactly the same as the one we've just done, okay? So add 1 to the power divided by the new power, and we would get the answer. So integrating 3 times the square root of x cubed with respect to x would have to be rewritten. I'd have to rewrite the square root of x cubed as x to the 3 over 2. Again, the square root, there's a little 2 there that's not written, and so it's 3 over 2, 3 over 2. Now the same rule applies. Add 1 to the power and divide by the new power. Look at, that's the solution, okay? What's happened? I've added 1 to the power. 3 halves plus 2 halves is 5 halves, and I've divided by the new power. We wouldn't leave this answer like this. We do something. When I'm dividing something by a fraction, then there's a step I always do, and I want to talk about why that works in a minute. You might well have thought, we talked about this before, 3 divided by something is the same as 3 times 1 over it, okay? The inverse, in other words. But I can think of 3 divided by 2 like 3 divided by 2 whole ones, 2 over 1. So actually, when I multiply, I'm inverting this fraction. 2 over 1 becomes 1 over 2. You might have heard when you're at school, one fraction divided by another. Can anybody remind me what you do? Yeah, you invert the second fraction and multiply. And then you can do it, okay? What I'm doing in this particular case is I am dividing by a fraction. So this is what you always do in these cases. You invert the bottom fraction. So 5 over 2 becomes 2 over 5, and multiply. So this becomes 2 over 5 times 3x to the 5 over 2 plus c. I've inverted it, and then it becomes a multiplication. And then I look at it and I say, actually, that 2 times the 3 on the top becomes 6. So it becomes 6/5 x to the 5 over 2 plus c. And I'll record this bit. If you're not sure how to do this bit, you can do it on the calculator. 3 divided by 5 over 2 is 6 over 5. It will do it for you, okay? Which is, of course, 1.2 x to the 5 over 2 plus c. So you could write it like that. And in an engineering situation, that's entirely acceptable, okay? I could do something with this x to the 5 over 2, of course, couldn't I, George? What would that be? Yeah, the square root of x to the 5 plus c. So I could write it like that. Integrate 3 over 2 to the power of 3 over 2 with respect to x. Yeah. So first stage, add 1 to the power, divide by the new power. So that's easy enough, okay? 3 halves becomes 5 halves. Divide by 5 halves. I'm dividing by a fraction, so what do? Yep, and multiply. So it becomes 2 over 5 times 3 over 2 x to the 5 over 2 plus c. And then I notice that the 2's cancel. So I'm left with 3/5 of x to the 5 over 2. So this equals 3 over 5 x to the 5 over 2 plus c. And if you're in doubt, you can do it on the calculator. What's 3 over 2 divided by 5 over 2 on the calculator? It will give it to you, but hopefully you'll see how to do it without. Can be written as that. Remember, we don't know what this is. You know, it doesn't. What does this mean? We'll have to talk about that. So at the moment, this is just the integral. So if you carry on down the page, it's this. Carrying on down the page, the integral of 3 over 2x to the 3 over 2 is this. So finally we could write integral of 3 over 2x to the 3 over 2 with respect to x is that. That's the answer, in other words. So for this example, we've now got a different type of function, a sine function, one of the trigonometric functions. And the rule we're going to apply is this rule here. I've taken this from the table of common integrals, or standard integrals they're sometimes called. All this rule is telling me is that if there's a number inside the trigonometric function, in this case that's a 2, that comes out and goes underneath. If you think about the differential, that number came out and multiplied. Now it's effectively coming out and dividing, which makes sense. Okay? And the sign becomes negative cos. So what about this number that's in front? Well, that just stays there. So in this particular case, the answer will be equals 3 over 2, but negative because that's what the rule tells me, cosine of 2x plus c. It could be written like this, all divided by 2 plus c. Okay? That's a common sort of thing that trips people up. These actually mean exactly the same thing, these two things. Dividing 3 by 2, or minus 3 by 2, and then timesing by this is exactly the same as multiplying minus 3 by cos 2x and then dividing by 2. The order doesn't matter. So integrate 4 cos 2x with respect to x. So there's the rule. A comes out and goes underneath if there is a number inside, and the cosine changes to a sine. The rest stays the same. Ax inside is unchanged, plus c. So hopefully in this case you got equals 4, because the 4 just remains there, over 2 sine 2x plus c. Can we tidy that up? Just 2, isn't it? 4 over 2 is 2. So I would expect you to do that. It would be silly not to. Would give you 2 sine 2x plus c. So last one, integrate 3e to the 4x with respect to x. Which rule applies? And then write down your answer. So there's the rule. It's telling me that if there's a number inside as well as the variable, in this case that's x, that comes out and goes underneath, and the power of e, the exponential function, just like in differentiation, stays exactly the same. So we end up with 3/4 e to the 4x plus c. Done.